Good morning and welcome back. Today I'm very happy because this is our last class. Next week, we will have your final oral presentation, and you should upload your final oral presentation to our e-learn system, or just give to our TA 张承轩. The same. Our TA will collect all the video file and we will evaluate your overall performance. Okay, so how about the day after next week? We still have that is June 16, special topic. We have another special topics. I will give you the file, give you some papers regarding to the course of this semester, so you can study by yourself. And then, if you want, you can return what you have learned, a paper, a report about what you have learned. Return a report to me, so you will receive extra bonus, 5 points at the most. Okay, if you care about your score, that's a pretty good chance. If you just care about pass or not, don't worry too much. Okay, so let's talk about our special topic 1. So first, that's plasma physics. Today is okay, PP21. Okay, we will talk about a special topics. That's electron cyclotron measure. Measure here. Look at here. What's the difference between measure and laser? Looks very similar. This is light. This is microwave. Okay. Actually, we have measure first, and then we have laser. But laser becomes very famous, so people forget about measure until recently. That's electron cyclotron. So electron is perform a cyclotron motion, circularly motion under magnetic field. Circular motion, cyclotron motion, something like that, under magnetic field. So we will consider magnetized plasma. Okay. We will consider here magnetized plasma with magnetic field. And the magnetic field is very strong, actually. Very strong. Very, very strong. 0. Wow. What happened? Magnetic field is very strong. Okay. So today we will focus on a very important topics. Relativistic velocity of equations. As we mentioned before, without relativistic effect, electron cyclotron, there is no instabilities. So I will show you with the relativistic, we will see something different, something unexpected. Our work will change from XV plane, from X velocity position and velocity space to SP space. P is momentum of a particle. Then the distribution function is here. F of XPT, implying that F of XPT is the distribution function, implying that FXPT D3X D3P gives the total number of particles in the differential volume in the small volume X and small volume P at point X and P and time T. For the same reasoning as discussed in section 6.1, the absence of collisions. So FXPT obeys an equation of continuity of the form here. Equation of the continuity of this form. That's continuity equation. Okay. And notation here divided into two parts. And divergence operator S dot P dot is the velocity and momentum change rate in a XP space. And we may derive the relativistic version of the velocity equation. The relativistic version of the velocity equation by exactly the form 1 here by exactly the same method used in section 6.1. The main difference is we now use the relativistic equation of motion. So it's relativistic equation of motion. Lorentz force is still the same, but here we change to this form. P is gamma mv. Okay, so in 1 here, change to divergence these two, divergence these two. Okay, so in short, we can rewrite this one. P is gamma mv as shown here. Gamma is relativistic factor. M is the rest mass. Okay, and you can skip the mathematical detail, and this part, this one operate on these two will be here. Okay. If you don't like this one, you can skip the mathematical detail and focus on here. Let's focus. Simplify the calculation, substituting 4 and 6 into 3. Then substituting the result into 1, we obtain the relativistic velocity equation. Yes, we saw this one before, and that's the major difference. We have force, and we have these terms. Okay, that's the major difference. Okay, The major difference is here. That's force. And remember, we have Lorentz force here, but we divided by mass m. Okay? Which can be interpreted as along a particle's orbit in the sp space, the particle density remains unchanged. So equation 7 is the most important equation we should remember at this moment. Okay, so you don't have to, if you do not have time, you just accept we have derived this one. Maybe similar to Belousov equations, non-relativistic Belousov equation. But now we change to relativistic Belousov equation. Just change from xvt to xpt, the variable, 6 variable, 3 space, 3 velocity, and time, to 3 space, 3 momentum, and time. That's the major difference. Okay, next one. We will use a complete set of equations. Complete set equation, of course, includes relativistic Belousov equation and 4 Maxwell equations. Divergence B equals 0, divergence E equals 4 pi rho, and here curl of E equals minus 1 over C partial B partial T. Curl of B equals 1 over C partial E partial T plus 4 pi over C times J. That's Gaussian unit. Okay, that's Gaussian unit. And rho is the related with here. Rho is related with this one. And J is related with this one times this one. Okay. Each particle species, because that's momentum integration. Remember, in the old time, we use velocity integration. But now, we use momentum. We use momentum, okay? Each particle species denoted by the subscript. If we have more than one species, 1, 2, 3, then just use the subscript alpha. For example, you have ion, you have electrons. So Q alpha carries the sign of the charge. Q alpha carries the sign of the charge. It can be positive or negative. Okay, it depends. Depends on the species. So the general form of the equilibrium solution is here. That's the general form relativistic Belousov equation. The same here, okay? So the general form, where the time differentiation dt follows the orbit of a particle. Follows the orbit of a particle. Thus, as in the relativistic case, any function of constant of motion, independent of time, is a solution of relativistic Belousov equations. The equilibrium solution, denoted by subscript 0 of interest, to us is a steady state solution founded of constant of motion. Constants of the motion with no explicit time dependent. No explicit time dependent. That is, depends on CP, but not depends on time. Explicit. ESP LICIT. Examples of constant of motion. Here are some examples. 1, B equals 0, E equals 0. So no acceleration, no cyclotron motion. Gamma, Px, Px are constant of motion. That's for sure. And another one, E equals 0. B0 equals a certain value, a constant value. Then we can separate into no acceleration. So gamma will be a constant. Perpendicular and PZ are all constant of motion. Okay. And because in a z direction, so we separate into PZ and P perpendicular. P perpendicular just means PS and PY. And PS, PY, these two are not constant of motion, but P perpendicular is. P perpendicular. Actually, the absolute value of P perpendicular. That depends on Px squared plus Py squared, square root. Okay. Yeah. So the relativistic motion of a charged particle, mass m, a charged particle mass m and charge q, in EM field, A and phi is also governed by Lagrange equation. You can check Ghostan, Poole, and Sokol, classical mechanics. Okay. So that is related to canonical angular momentum. Canonical angular momentum. Okay. As a side note, okay, actually you can find an this is angular momentum, and we add these terms, these extra terms. So we call this canonical angular momentum. As a side note, the constant of motion in 16 is a useful quantity to monitor the accuracy of numerical calculation of the relativistic particle in motion. In electromagnetic field, relativistic particle motion in electromagnetic fields. Actually, our recent paper published in IEEE transaction on electron device. We published a paper this year, last year, sorry. A paper in this journal, IEEE transaction on electron device. That's a pretty good journal. This journal, we talk about canonical angular momentum of a new electron gun. This new type of electron gun use the idea of non-relativistic, use the idea of non-adiabatic. So people always think non-adiabatic is not a good idea. It's difficult to control, but we show, no, it's not that difficult. It's actually controllable. Examples of equilibrium distribution function. Examples of equilibrium distribution functions. As in chapter 6, we assume that the plasma is immersed in a uniform external magnetic field along the z-axis. Okay, magnetized plasma immersed 浸在 but there is no external E field. Okay, we have B field but no E field. So an equilibrium solution F alpha 0 P must satisfy the zero order relativistic Blasov equation, which for our model is here, independent of time and independent of position. And this is 0. And this one times this one. So we have this one, 0. Thus, any function of the motion satisfy equation 17, provided that the total charge and current distribution of all species vanish, so that there is no net self-field, at equilibrium. Total charge and the current density of all species vanished. That means total charge that vanished. So therefore, no electric field. Total current vanished. Therefore, it don't generate magnetic field. That's why we say that vanished. This in turn makes P perpendicular and PZ constant of motion in the only fields presented. The only field present is B0 in the Z direction. In fact, the demonstration in equation 17 is redundant. 多余的. Since we have already known, we have already shown that any function of the constant of motion is an equilibrium solution. Okay. For a weakly relativistic plasma, here is the weakly equilibrium plasma. Weakly relativistic plasma, the Maxwellian distribution functions normalized to N0 can be approximated at this one. PT is the thermal momentum. And the bi-Maxwellian, strong Maxwellian distribution, for example, 两个 momentum by Maxwellian, just like by temperature. When we perform the integration about P, we will obtain total number of particles will be N0. We may also have an equilibrium distribution function of the form. That's another expression. Actually, we will use this one or use this one, which represent a uniform distribution N0 of particles in random phase gyrational motion with perpendicular P perpendicular 0 and PZ 0 for all particles. Okay, so after the integration, we have only one value, N0. Okay, makes sense. Makes sense. Note that. Be careful, F0 of P above here has the dimension of N0 divided by P squared, while S, the non-relativistic, has the dimension N0 divided by N0 over v cubed upon this and this integration respectively. Both give results of the same dimension, n0, particle number. Okay, makes sense. So how about the first order equation? We have the zero order relativistic particle orbit. We have zero order. How about first order? To obtain the, let's have a 30 minutes break. Okay. And drink some tea. To obtain the first order solution of 7 by integrating by part, integrating over the unperturbed orbit. As in section 6.10, we need the zero order orbit of the particle in magnetic field. So we begin with a derivation of the relativistic zero order orbit. Actually, we already did that before for non-relativistic. So for relativistic, just slightly change. Since gamma is a constant of motion, because in static magnetic field, so gamma should be, Lorentz factor should be a constant of motion. We may write the relativistic equation of motion here. And V, you can write into, if you, with respect to V, with respect to V, shown here. So we change to this form. We have two expressions. We have omega alpha here. That's the traditional non-relativistic. But with relativistic correction, we have R here. In terms of notation, rest mass, spectrum frequency. Spectrum frequency. Rest mass spectrum frequency. Okay, that's non-relativistic. That's relativistic. Okay, so luckily we have this equation, equation 21. This has the same form as 1.24 of chapter 1, plus under the condition x prime equals x and under the same time, we have this one. The major difference is here. See? One, two, three, 4, 5, 6, 7, 8. 8. Relativistic spectrum frequency, non-relativistic spectrum frequency. Relativistic effect has only results in the replacement of the rest mass. You can say that. Replace the rest mass with the relativistic mass. Others are the same. Just change the rest mass here to relativistic mass. So here, change from M alpha to gamma M alpha. Okay, looks very simple. Then we have zero order particle orbit. Zero order relativistic particle orbit. And we should write the first order and particle dynamics. 粒子的动力学 particle dynamics. So we will consider force. We treat the particle dynamics by assuming small perturbation, small perturbed quantity. It allows us to linearize. Remember, we always use linearization, the set of Vlasov-Maxwell equation. That's the zero order. That's the first order, zero order, first order. And remember, no zero order, otherwise we will generate electric field. We just have first order only, these two, just first order only. Substituting the zero order terms into 24, equation 24, the Vlasov-Maxwell equation. Which is satisfied by any function of the form provided here. Zeroth order, 0, zeroth order, 0, and here, okay? Zero order. Okay, that's a basic knowledge, background information. Substituting all terms in equation 24. Equation 24 here. Substituting all terms in equation 24 into the Vlasov-Maxwell equation. And then equating the first order terms. 把第一阶的找出来，那第零阶的已经自然而然是正确了。把第一阶的找出来 ，first order terms， we obtain the first order equations here. First order. Sorry, then zeroth order, first order here, and first order, zeroth order. So it's first order and first order. Okay, so it's a first order equations. Zero order equation already correct. And real order equation allow us to calculate V and X position and V, okay? That's important because here we will use V again. To calculate V, you need the knowledge of X. So we can rewrite this equation into this form. Okay, that's the Vlasov equation. That's first order, but first order is related to here. Very similar, right? Very similar. That's the Lorentz force. So the left-hand side, right-hand side is very similar. Left-hand side is a total derivative, a total time derivative along the zero order particle orbit. 你就随着粒子的轨道，你就会发现这个式子，这个左边的这个是一个全微分， total time derivative. Because the acceleration force, to sexual motion, centrifugal force, hence the right-hand side of equation 25. That's the equation 25 is to be integrated along the zero order orbit, and gamma is a constant of integration, which gamma is a constant because magnetized plasma without E field. So we have this one. We can rewrite into this one and this one. Okay, so no big deal. We just rewrite this equation into perpendicular, and E phi and EZ separate into 3 parts as perpendicular in the perpendicular directions. We separate into X, Y, and Z. So here, for our convenience, we just separate into 2 parts. Actually, personally, I prefer this form. This one and this one. Remember, gamma is a constant. So slightly change with this one. That's equation 32. We just simplify, we just use a notation here. Oh, just a moment. Okay. Equation 32 is easy to understand. Oh, just a moment. Where is my okay. Substituting this equation, equation 32 into 25. What will we have? We have this one. Yes. 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 3 parts. Okay. Substituting this one, we have these properties. We have gamma m alpha, and this one together with this one. What's the major difference with non-relativistic? Here, gamma m alpha, and gamma m. So very similar. We just change m alpha to be gamma m alpha. We found that except for the dimension of f alpha 0, the two equations differ only in the multiplication factor gamma on m alpha in equation 33, which is the same difference between the relativistic and non-relativistic orbit equations. Thus, this solution of equation 33 is simply the non-relativistic solutions, with m alpha replaced by gamma m alpha, and f alpha 0 be perpendicular here by here. Note that in equation 162 of chapter 6, f alpha 0 is contained in the dimension of SYZ. Okay. One more time. Relativistic, non-relativistic. The left-hand side, the same. Right-hand side differ by gamma. Okay? Throughout the derivation of the non-relativistic dispersion relation, there are only two quantities which contains the rest mass m alpha. One is the cyclotron frequency. The other is the plasma frequency. Cyclotron frequency and plasma frequency. For later convenience, we will retain the above notation for the rest mass, cyclotron, and plasma frequency, and write the relativistic cyclotron and plasma frequency as here. Oh, relativistic plasma frequency, relativistic cyclotron frequency. Okay, that's plasma frequency, that's cyclotron frequency. The dimension difference between this one and this one is shown here. Very similar. Will be rectified when we carry out the integration. Rectified when we carry out the integration to obtain J1 and subsequently the dispersion relation. Because in a non-relativistic formalism, we have used this integration, but now we change to this integration, momentum integration, not velocity integration. Okay, so a relativistic dispersion relation for a plasma in a uniform external magnetic fields. Okay, so now let's consider a case, relativistic dispersion relation for a plasma. Okay, based on the discussion above, we have the following recipe for converting the non-relativistic dispersion relation for a plasma in a uniform external magnetic field B0 EZ into a relativistic one. In any of the equations, replace m alpha with gamma m alpha and cyclotron frequency omega alpha q alpha B0 over m alpha c with omega alpha over gamma, and plasma frequency omega square p alpha equals 4 pi n0 n alpha 0 q alpha squared m alpha with omega square p alpha over gamma. Note, if there is an integral, gamma must be part of integrand, because gamma is a function of p perpendicular and pz. Okay, gamma must be part of integrand because gamma is a function. gamma 不能直接拿出来哦，伽马必须在积分的那个因子里面哦。Replace the integration symbol with a symbol here. Replace this one with this one. All other quantities, such as V perpendicular VZ, remains unchanged. Because we may interchange V perpendicular with V, we just interchange. This one. Okay. Okay, looks good. A specific example. Rewrite the dispersion relation for right circularly polarized waves. 右旋、右圆极化波 右旋极化。Okay. Let's the old expression non-relativistic. Step 2. Step 1 and 2, we get the relativistic version. 很简单 ，omega square 不变，这个地方也不变，这个地方也不变，这个 plasma frequency 变成这样子，这个地方不变，这个地方不变，这个地方不变，这个地方也不变。relativistic effect 改成这个样子，这边，应该，OK 有没有写错嘞 ？V 垂直成长OK 没有错，没有错，看起来有点怪，但是 it's OK, no problem. Well, by step 3, it's understood F alpha is changed to this one. By step 4, we replace V perpendicular with this one. VZ with this one. What else? The same. V perpendicular. Gamma is moved to here. Normally, people don't. Gamma is, remember, gamma here must be part of the integral because gamma is a function of. 也就是说，伽马不能把它移到外面去，伽马必须在积分的 factor 里面 ，OK。然后这边 VZ 换成这样子 ，VZ 换成这样子。还有什么需要换的吗？这边不用，这边换成这个样子。好的。然后这边也换掉 ，OK， 已经换的差不多了。That's step 3. Rewrite equation 35 in slightly different form and neglect the ion. We just consider electron and omit or neglect. 忽略 ions， 为什么要忽略 ions？ 因为 ion 的速度太慢了，我们只要考虑 electron 就好。So the equation becomes here, just one species. That's equation 36. And gamma is related to here. See the relativistic between 5 and 6. We have, partial gamma, partial perpendicular actually has contribution. Partial gamma, partial PZ also has another value. Partial 1 over gamma. Okay, that has contribution because here, just substitute these 4, equation 37, okay, into equation 37. Integrating 36 by parts and using, 我们用 integration by parts, 用我们的知识 equation 37的知识带进去 we obtain some algebraic manipulation, 一些几何上的操作，我们最后就会得到这个式子 similar. Okay, not exactly. Equation 38. Okay, let's rewrite equation 38. equation 38 here, integrating 36 by parts, we have differential gamma with respect p perpendicular and pz, which it should be which WHICH, which brings out the relativistic effect in the sense that the relativistic mass m gamma me depends on p perpendicular and pz. Terms arising from these differentials can be combined into a single term proportional to omega squared, as appeared on the right-hand side of equation 38. Okay. We now specialize to, we have a distribution. Just assume the ideal case. The ideal case. Last equation 38 with that's cold beam. Why we say it's cold beam? Because no thermal distribution do not depend on temperature as the ideal case, delta function. So we call it cold beam. Equation 38 reduced to a simple dispersion relations given by this one. Where gamma 0 and V perpendicular 0 are equilibrium value of gamma and V perpendicular, respectively. Okay, interesting. Rewrite equation 39 again. Okay, that's equation 39. The non-relativistic version. See, what's the difference? Here, 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 gamma, anything else? Extra term. This is an extra term. Okay, that's the major difference. Major difference. Which was also obtained for the right-hand circularly polarized wave. And for a similar equilibrium distribution, comparing the two expressions, we found that the plasma frequency and cyclotron frequency are both modified. Plasma frequency, cyclotron frequency are both modified, okay? By the relativistic factor as expected. In addition, equation 39 differs from the non-relativistic version by the presence, differs from by the presence of these extra terms here. This term has been shown to be part of purely relativistic origin. 这个纯粹是来自于狭义相对论的。Here. Equation 39 is plotted on the next page for this case. And gamma 0 equals 1.10 keV, 小，能量很低。And V perpendicular just 0.2 c, the speed of light. Along with如果是100 keV 的话 here is an 100 keV, sorry. 如果是100 keV, 这个地方就会 gamma 就会变成 1.2， 然后 v perpendicular 就会变成 0.55C。 OK， 所以你看10000伏特的电压，你就可以产生 0.2 speed of light， 还蛮容易的。OK, next one. In the relativistic model, both the slow and phase wave branches are unstable, which means omega is complex and exponential growing in time. However, in a non-relativistic model, only the slow wave branches is unstable. Non-relativistic model here. That's phase wave, that's slow wave. And non-relativistic model, only the slow wave branch. Omega I is non-zero. Obviously, the relativistic effect is responsible for the phase wave instability. Phase wave instability, which is driven by energetic electrons through cyclotron resonance. The physics mechanism will be discussed next. 你看，有用狭义相对论跟没有用狭义相对论。没有狭义相对论，根本就没有。有狭义相对论，才会冒出这个东西来。Let me tell you a short story. 在1950几年的时候，所有的科学家都认为是这个，但是1955年、56年的时候，有一些科学家把狭义相对论考虑进去。在那时候，他才发现，如果考虑狭义相对论的时候，它会冒出一个 phase wave 的 instability。phase wave 代表 phase velocity omega over kz 大于光速phase velocity 大于 speed of light， 这时候竟然会有不稳定性，这不是很奇怪吗？所以很多科学家尝试说他们做错了，可是结果是他们是对的，而且引领了下一个潮流。因为有 phase wave 的 instability， 导致新的物理被发现。That is, let me show you. Electron Cyclotron measure 变成 gyrotrons. Okay. Here is the physical interpretation of phase and slow wave instability. We have effective cyclotron frequency. The electron wave resonance condition is here. Beam wave, actually we prefer beam wave resonance condition, which implies that the electron sees almost a static wave, E field, and hence lose or gain energy for an extended period of time. Omega EFF. That's effective cyclotron frequency, which governs the degree of synchronism of each electrons with respect to the wave. In equation 42, a change of gamma, hence the relativistic cyclotron frequency, omega E over gamma, affects the synchronism, 同步性, as expected. In condition, since the wave phase varies with z, vary with z, a change of Vz affects the electron's z coordinate. Hence, also the electron synchronism with the wave. Okay, we still have 5. Oh, don't worry, very close to the end. We still have 4 pages. And effective cyclotron phase function. Let's read. Since this one is independent of phi, it represents a uniform distribution of electrons along any cyclotron orbit. Thus, for every electron which gains energy from the wave, another electron will lose. Well, one gain获得能量 gains energy from the wave， 从波那边获得能量，另外就有一些会 out of phase， 会损失能量。This results in zero energy exchange between all electrons and the wave. So to have a net exchange of energy. 这边就是大家认为不会有50%会得到能量，50%会失去能量 ，50-50。50%会 gain energy， 另外50%会 lose energy。那就没完没了啦。So to have a net exchange of energy， 如果要从电子的动能取得能量的话 ，the electron must first have bunched, which give rise to an AC current. 哦，如果从这个角度来看的话，大家你50我50，所以没有。可是事实上不是哦。那怎么样让它不是呢？ It's convenient to visualize the electron bunching by keeping track of each electron's variation in omega EFF. If, for example, of all electrons remains at their initial phase and gamma 0 respectively, omega effective will be constant for all electrons. Thus, no bunching occurs. Bunch 是群聚现象 ，bunching effect。为什么会发生群聚？粒子为什么会发生群聚？我们有些加速，有些减速，加速走得快，减速走得慢。如果在一群粒子里面，前面是减速，后面是加速，那就形成一团。OK， 它就可以把原来是直流的变成交流。However, Vz and gamma will have different variation in the wave fields, causing the electron to bunch in effective cyclotron phase space. What's that? Okay, actually, this is the most important part of Maser. Most important part of Maser. Okay. Rewrite here this equation and effective cyclotron frequency here. In the presence of a wave, Vz and gamma will vary according to this one. OK， 有了哈，这个 first order， where E perpendicular and B are wave electromagnetic fields, which we denoted as perpendicular, because they are perpendicular to EZ. The increment 一个小小的增加 of cyclotron frequency over an infinitesimal time interval delta t， 这边的改变呢 在小小的时间内的改变，这个还有这个变成这个加上这个 ，where delta Vz may be evaluated from the z component。delta Vz 跟 z component 有关 ，OK， 所以跟 z component 有关，所以跟这个是有关系的。我们可以把这个东西这个换上 ，we have substituting， 所以 delta Vz 其实是跟能量变化有关系的。OK， 这边开始有趣咯，要分析 bunching mechanism。The charge of gamma is determined by the work done by the electrons, delta gamma. Here, delta gamma. And delta gamma 跟它做的有关 ，and Vz 跟这个有关，所以 cyclotron frequency 跟什么有关？跟这个有关。Where we have made use of these relations， 我们就假设它们靠得很近哈 ，and Vz equals 0。The terms of proportional to omega square and kz square are due to delta gamma。我们把它分作两部分，一部分是来自于 delta gamma， 一部分是来自于 delta Vz。OK， V perpendicular dot E perpendicular are different from different electrons. Bunching occurs. Furthermore, the two terms are jointly by a minus sign, indicating the two branch mechanisms are compete. Oh, compete. 这两个是互相竞争的。事实上，一个叫做 S-mutual bunching， 一个叫做 axial bunching。Okay, since the two bunching mechanisms are competitive, the non-relativistic model overestimates the growth rate and of the slow wave instabilities, which appears as we compare the non-relativistic and relativistic slow wave. As we consider the relativistic and non-relativistic slow wave growth rate in the figures of few pages back. 在前面几页的时候 ，Equation 48 also shows that the relativistic mechanism dominates for phase wave. 狭义相对论的机制在快波的时候是很重要的。While the non-relativistic mechanism dominate for the slow wave， 在慢波的时候，非狭义相对论是很重要的，主要的。OK， 那这就我解释了为什么在边界的时候 no growth rate。这个我会给大家几篇论文，让大家可以看我们这个 special topic。其实每一篇都很重要，每一个都会用到。这几篇论文把我们所提到的这几个逻辑讲得非常的清楚，你只要选择一篇来写报告就可以了，看懂写报告就可以了，所以不需要多。或者是你去看一下这个期刊，这篇论文朱国瑞院士写的 The Electron Cyclotron Measure published in Review of Modern Physics， 在2004年，这个 impact factor 大概有38，非常高 ，citation 是非常非常高的， 几乎在这里面的每个都要看，因为这里写的非常的清楚，非常的清楚，非常的明白。这个是一个经典的期刊，经典的论文，我建议大家仔细读一读。OK， 那我们 Plasma Physics 的课就到这边结束，接下来会让大家做一些 self study， 然后写报告，还有下礼拜请记得把你的 oral presentation， 事实上是12分钟了，12分钟的 oral presentation 交给助教或者上传到 e-learn 的 system。OK， Thank you and see you next time。拜拜。